Today I am going to discuss about bench rule, one of the most important topics in chemical bonding. Okay, before I write bench rule, first let me ask some questions or let me show some structure, and then you will understand the need of bench rule. So before, okay, need of bench rule. Why there is a need of bench rule? bench rule এর প্রয়োজন কি? bench rule কোথায় লাগবে? কি জন্য bench rule আমার লাগবে? Okay, first let me ask you some questions about these structures. This structure, there are lots of molecules. Okay, in these molecules both lone pair and bond pairs are there. Both lone pair and bond pairs are there. Lone pair আছে, bond pair আছে. Okay, let me take the example of SF4. Okay, SF4. In case of SF4, total valence electron, if you count, then it will be 6 plus 4 multiplied by 7, that is 34. 8 2s are 32, 2 1s are 2. Okay, so steric number is 5. Okay, steric number is 5 for SF4. It means that sulfur is here sp3 hybridized. Okay, sp3 dehybridized, sp3 dehybridized. Okay, if you look at the structure of SF4, then there are 4 sigma bond pairs, and one lone pair, right? 4 sigma bond pairs and one lone pair. Now question is that where we will put the sigma bond pair and lone pair. SF4 molecule has TBP geometry, trigonal bipyramidal geometry. Okay, let me show you the trigonal bipyramidal geometry. Okay, say this is sulfur. Now if you write the structure of SF4, isn't it look like S? Okay, F and one lone pair of electron. Fine, perfectly alright. Now question is, which two positions are different? Here there are two positions basically. This form equilateral triangle. These are the equatorial positions. There are 3 equatorial positions, and here angles are, you know very well that angles are here 120 degree. This is 120 degree, and this is also 120 degree, and here it is 90 degree, and here also it is 90 degree. So two types of angles are there. 90 degree and 120 degree, and 2 types of positions are there. This is one positions means equilateral triangle trigonal plane, and this one basically axial position. So 2 positions are there, axial positions, and this is equatorial positions. Now question is, where you will put the lone pair of electron and where you will put the bond pair of electron? Can you put it arbitrarily anywhere to get the shape of the molecule? First of all, of course no. It is not possible. You cannot put lone pair or bond pair anywhere. You must put in a certain locations or certain positions to get the stable structure and get the exact shape of the molecule. I mean, you have to put the lone pair or bond pair in such a way that the molecule will have the minimum repulsions. It will minimize the repulsions after it put the lone pair and bond pair of electrons. Okay. From here, actually, we need the Bain rule. Basically, for this we need the Bain rule, that where to position the lone pair and sigma bond pair or a double bond also. কোথায় lone pair রাখবো, কোথায় bond pair রাখবো, that is very important. You cannot put it anywhere. যেখানে খুশি আমি দিতে পারবো না. Not at all possible. Okay. Say, if someone puts lone pair of electron like here, okay, here, and if like this, someone might put lone pair let's say here, but both are not the correct shape for SF4. One is correct and another is incorrect. একটা ঠিক একটা ভুল, সেটা কি করে দেব? Bain rule successfully explain this one. If you know the Bain rule, then you can easily tell that where to place the lone pair, where to place the bond pair of electrons. Here I have shown lots of structure. Okay, after SF4, if I take another example, say take the example of ClF3. In ClF3, if you calculate, you will get basically two lone pair and three bond pair, two lone pair and three bond pair. And hybridization is beta hybridization क्या है? ये hybridization है sp3d. The hybridization of central chlorine will be sp3d hybridizations. Okay. Now what about these two lone pairs? Now if I show the geometry, it's a confusing. Can I put lone pair here and here and F here, or can I put here here? See, both the same are incorrect. This is not true. This is not true. Okay, in order to know the hybridizations, you just first calculate total valence electron. Many times I mentioned in my earlier video, and then divide by 8. That will give you the divide by 8. That will give you the basically the number of lone pair and sigma bond pair. Okay, right? This is sigma. So how can you say that these two shapes are incorrect? That's my Bain rule. Okay, one lone pair, two lone pairs. Then next move to a structure like HCF2. If you get the hybridizations of xenon in HCF2, it will be basically sp3d that you can calculate. sp3d 8 plus 2 multiplied by 7, 8 plus 14, 22, 8 2s are 16, 6, 2 3s are 6. So 2 1 pair, static number 5, 2 1 pair plus 3 lone pair. Now again question is, I have to put this one. Sigma bond pair and lone pair. Can I put sigma BP? Can I put like this? Okay. Lone pair here, F here, and one more lone pair here. Can I put it? No, you cannot. Arbitrarily, you cannot put. See, once you will know the bend rule, you can easily draw the shape successfully without facing any problems. In no time, you can do it. Now, if you say move to like this one, XCF4 or XCF4, okay, first XCF4, this is sp3 d2 hybridized. So there are basically 4 sigma BP plus 2 lone pair of electron. Geometry is octahedral geometry. So this is xenon. Now again question is, where you will put this sigma bond pair and lone pair. Okay. One more, that is XCF5 minus. XCF5 minus, beta, total valence electron if you calculate, then 8 plus 5 multiplied by 7 plus 1, that is 42. 8 5s are 42. Okay. Okay. This will be 44. Okay. This will be 44. So 44, 2, 2. Okay. So static number 7, hybridization is sp3 d3. Geometry will be pentagonal bipair. Okay. Write XC here. Again questions. I had to put the lone pair of electron, and I had to put this lone pair, and I had to put this sigma BP, means fluorine atom. This is the question. Now I am going to now discuss bend rule. Bend rule explain these successfully, and without any problem you can put the sigma bond pair and lone pair, and you won't face any problem while drawing the shape of the molecule. Okay. Now what is bend rule? So in order to explain this one, we need bend rule. Now I am going to discuss about the bend rule. What is actually bend rule? Okay. First, let me write the bend rule. Bend rule says that more electronegative elements prefer to occupy a positions where percentage of S character is less. What it says? The more electronegative element prefer to occupy a positions where percentage of S character is less. It means the electronegative element, more electronegative element in compared to other element, will preferably positioned in a orbital where percentage of S character is less compared to the other orbitals. And one more statement, that lone pair occupy positions where percentage of S character is less. Sorry. Percentage of S character is more. Lone pair occupy positions where percentage of S character is more. Means lone pair will preferably occupy a positions where percentage of S character is very high. These are the two statements of Bent rule. From these two statements, we can easily draw the shape of the molecules which I have shown just now. Okay. Now question is, why more electronegative element prefer to occupy positions where percentage of S character is less? It is little bit, it seems that it is little confusing for you. Okay, let me explain both these statements clearly, then we will go for drawing the structure. Okay, more electronegative element prefer to occupy positions where percentage of S character is less. See, till now we have idea like, say this is a tetrahedral geometry. So this is CH4. Let me take CH4. So carbon is here, sp3 hybridized. Carbon is here, sp3 hybridized. That means 4 sp3 hybridized orbitals. 1, okay, 2, 3, 4. Now if I ask you, in these hybridized orbital sp3, percentage of S character, how much here? Okay, sir, 25% and 75% P character. This is here also, sir, 25%. Here also 25%, and here also 25%. Yes. Thing is that if we have a molecule where the substituent, if any of one of the substituent get changed, then hybridizants in sp3, this hybridized orbital or one of the hybridized orbital, if there will be one substituent, won't have 25% S and 75% P character. It will change. What do you mean? I am trying to mean. Okay, let me do one thing. Say if I replace this hydrogen by one fluorine, then what will happen? Okay, you cannot now say this carbon is sp3 hybridized, 4 sp3 hybridized orbitals are there, 1, 2, 3, 4. You cannot now say, till now we used to think like, okay, 25%, 25%, 25%, 25%. So no. This is the beauty of Bent rule. Here percentage of S character, here percentage of S character will be less. Why it is less, that I am going to discuss very soon. Say you are expecting 25%. Okay, I am telling you that instead of 25%, I am saying it reduced to 19%. It reduced to 90%. Means 6% reduced. Okay, means 6% reduced. This 6% won't go anywhere. It will go to these three hybridized orbital. It means here if it's 19%, here it will be 25 plus 2%, 27%. Here also 27%, and here also 27%. If you count now, 27 means 81% plus 19%, that will give you 100%. No problem. Previously it was also 100%. 25 expected, like 25. But it's not like that. This is the beauty of Benn rule, that whenever there will be symmetry will lost, mean different substituent will be present, the percentage of S character will get changed entirely. However, if the substituents remain same, that won't change the percentage of S character. Okay, let me show you one more example. Like, say, see, this is F, this is F, this is F, this is F. Now, if I ask you that what is the percentage of S character here, say all are fluorine atom. This is symmetrical structure. So percentage of S character in every hybridized orbital, it is 25% S character. 25% S character. It's clear? 25% S character. However, if we replace any group, any atom here, then what will happen? Percentage of S character will change. Now, let me explain that why percentage of S character basically changes. Percentage of S character changes. And the statement of Benn rule, it was like mode electronegative element. Okay, in brief I will write mode electronegative element prefer a orbital where percentage of S character is less. This is the statement. Now question is why? Let me explain that one. Okay. When we will be getting like sp3 hybridized orbital, how we will combine S plus P? That will give you sp, S plus 2p, sp2, and S plus 3p, that will give you sp3. Okay. Same. Now look at it here. This is S orbital. This is S orbital. Now I am going to combine S plus P. If I combine S plus P, then how does it look, that hybridized orbital? Look at very carefully. That hybridized orbital looks like this. This is the sp hybridized orbital. For sp2 hybridized orbital, how does it look? Okay. S plus 2p means px plus py. That will be this is sp2, no problem. Now sp3, S plus 3p this is like sp3. No problem. So this is S, this is sp, sp2 and sp3. Okay. After that, if you draw the shape of p orbital, it is like this. This is p orbital. Okay. Now let me show you one thing. That as you move from S to sp3, as you move from S to sp3, can I say that orbitals, hybridized orbitals get longer and thinner. So from here we can write this is longer and thinner. Longer and thinner. Okay, no problem. Okay. Now let me tell you one thing, that out of these 4 orbitals, 1, 2, 3, 4, 7, 5. Okay, this one also include 1, 2, 3, 4, 5. Out of these 5 orbitals, if fluorine wants to attach or form the bond where it will comfortably form the bonds, that is your questions. Say, say this is S. Okay, this is sp. Okay, this is sp2. Okay, this is sp3, and last one basically p orbital, like that. Correct? Okay. This one. Okay, no problem. Okay. Now let me tell you one thing, that out of these 4 orbitals, say fluorine will attach. So fluorine will form a bond here. Say this is fluorine electronegative element. This is fluorine electronegative element. This is fluorine electronegative element. This is fluorine electronegative. Say unhybridized orbital won't form the bond preferably compared to the hybridized orbital. So I am not going to show the bond formations with S and P. Remove that one. So pay attention only this one, and this one. Now this is the bond pair overlapping zone where electrons are present. Okay. Now see, fluorine is the one of the most, strongest electronegative element in the periodic table. Fluorine, strongest electronegative element. Its electronegativity is very high. Pauling scale, its value is roughly 4.0. Now, what fluorine needs? Fluorine will try to get the maximum delta minus in covalent bond. Then only it will be happy, because beta, I am the strongest electronegative element in the periodic table. I won't allow anybody to attract the shared pair of electron. Rather, I will attract the shared pair of electron most. I won't allow other element to attract the shared pair of electrons. The thing is that if fluorine has an opportunity, say here, or here, what fluorine will try to do? Fluorine, wherever there is an opportunity, fluorine, what it will do? It will try to form the bond with less S character. Means here it is sp3, it is sp2, and this one sp, this is S. Fluorine will try to form the bond with sp3. Say, if it means fluorine will try to increase the p character. More the p character, The orbital having more the p character, fluorine will form the bond. Fluorine will be very much happy because I will be here get maximum delta minus. मैं भाई काउ के डेल्टा माइनस আমি দেব না, আমি এখানে ম্যাক্সিমাম ডেল্টা মাইনাস আমি নিতে চাই, আমি ডেল্টা মাইনাস ম্যাক্সিমাম নিতে চাই কারণ আমার ইলেকট্রোনেগেটিভিটি হচ্ছে হাইয়েস্ট। I have the maximum power to attract shared pair of electron. That means wherever it will get an opportunity, means it will try to elongate the hybridized orbital and incorporate more p character so that it will be happy. Like here, fluorine don't want to be here in comparison. Fluorine chaive, fluorine wants that beta I will be happy here. আমি যদি এখানে থাকি, if I form bonds, then these shared pair of electron, these shared pair of electron, these shared pair of electron, I will attack maximum. Why? Because if it's carbon, carbon is here far away from the shared paired electron. Here carbon will attract the lone pair of electron. This pair of electron very high because it is closer to nucleus. sp hybridized orbital closer to nucleus. That's why more electronegative element, here I am taking the example of F, more electronegative element will try to occupy positions where percentage of S character is less. After that, adjustment will be done. If in one hybridized orbital the percentage of S character reduced, fluorine will reduce the percentage of S character, and that reductions of S character will be distributed in other hybridized orbital. S character won't decrease overall. In one hybridized orbital it will decrease, and another 3 or 4 whatever the hybridized orbital will be present, it will be equally distributed. So there won't be any loss of hybridized orbital, means the percentage of its character. Okay, that's why more electronegative element will occupy positions where percentage of S character is less. Here percentage of S character, here percentage of S character 50%, here 33.33%, and here it is 25%. And interestingly, now if I show you, like, okay, this is S, this is SP, this is SP2, and this is SP3. Okay, so this is SP, this is SP2, and this is SP3. Here fluorine, here say fluorine, here say fluorine. Okay, okay, so what I told you, that fluorine will be more happy here than here or here, means fluorine will adjust the percentage of S character. Okay, if I show you an example, let me show you an example. Say this is C, H, 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 and this is F. So before Bell rule, what you have an idea that it is 25, it is 25, it is 25, it is 25. No, what I told, fluorine will adjust. Fluorine will adjust means fluorine will decrease the percentage of S character here, means the orbital will get thinner. So say here instead of 25% it is say 19%. So here it will be like here and here and here. In these three hybridized orbital 2%, 2%, 2%, so will be increased. So this value will be like here 27%, here also 27%, and here also 27%. So that's why more electronegative element will occupy in a positions where percentage of S character is less. Now, what about the lone pair? What about the lone pair? See, I told you that lone pair will occupy a positions where percentage of S character is high. Try to occupy in a positions where percentage of S character is high. What does it mean? Okay. See, if I show you like again the earlier structure, like this is sp hybridized, say this is sp2 hybridized, and say this is sp3 hybridized. Okay, orbital get elongated. More the percentage of S character, it will be thicker. Okay, now if I tell you that, see, lone pair, first of all, it will be under the influence of only one nucleus. Under the influence of nucleus. Under the influence of one nucleus. One nucleus. So, however, the percentage of its character will be more. The lone pair will be more stable. What do you mean? What does it mean? It means, say, I'll put lone pair here, I'll put lone pair here, and I'll put lone pair here. Lone pair will be happier here because here percentage of its character is very high, 50%, it is 33.3%, and it is 25%. It is SP, this is SP2, and this is SP3. So lone pair will be more happy here. Okay, because more the percentage of its character, it will be more close to the nucleus. Means more the percentage of hybridized orbital of having S character, lone pair will be more stable. Say if you say the radial distributions functions versus distance from nucleus, what you have observed, 1s, 2s, 3s, 4s, you will get the probability of finding the electron near to the nucleus for any s orbital. 1s orbital, it will be like this. 2s orbital, it will be like this. So near to the nucleus, probability of finding of electron will be there. In case of 3s, it's like this, something like this, something like this. Maybe it will be separated. Whatever. However, for p orbital, it will be like this. So near to the nucleus, maximum probability of finding electron will be maximum probability of finding electron for s orbital will be maximum, not for p or d or f orbital. Okay. So lone pair will be happy with more percentage of S character based orbital. See, if it's still not clear, let me give you one example. Say, okay, HC triple bonded CH and HCH double bonded CH, acetylene and ethylene. Take this example. Let me show you that if you remove this hydrogen and form the conjugate base, then what will happen? The negative charge will be in sp hybridized, and here it will be in sp2 hybridized. Here it is in sp2 hybridized. Say this is sp2 hybridized orbital electron pair. This is sp hybridized orbital electron pair. You know, it is closer to the nucleus. This conjugate base is more stable. Compared to this one. That's why lone pair will try to be in a hybridized orbital where percentage of S character will be more. Okay. Now question is say, see how to check the percentage of S character if the angles are different for different angle. How you can check the percentage of S character? See, there is one formula. That formula, let me write that. Cos theta is equal to S divided by S minus 1. This is the formula. So if you put the theta, then you can easily calculate the percentage of S character. Okay, let me tell you now one thing, that sp, sp2, sp3, sp3d2, these hybridized orbital are symmetrical hybridized orbital. Means wherever you put lone pair or a bond pair, it won't create any problem. It's a very easy. Means if you take say sp2, if someone put say here lone pair and here bond pair, okay, it's perfectly all right. Okay, someone for sp3, say someone for sp3 or hybridized orbital put lone pair here, bond pair here, bond pair here, no problem. Or else you can put lone pair here or lone pair here. It won't create any problem. For sp3d2, the structure, I mean the geometry, it's like this. Say this is A, central atom. Okay, this is sp3d2 hybridized orbital. 6 hybridized orbitals. 1, 2, 3, 4, 5, 6. Okay. Now, lone pair and bond pair you cannot put arbitrarily anywhere. That I have told you. Now, in case of octahedral geometry, say you need to put one lone pair. Where you will put? Okay. If you put it here, okay, I wish to put it here. Okay, it's okay, no problem. If someone put lone pair like here, okay, somewhere here, and someone put lone pair, say this is A, lone pair, say it's a here. Now, is it okay to put like this way? Okay, no problem. Because here, all the bond angles are same. This is 90. It won't create any problem. But all the bonds angles are same. And this is also 90 degree. This square plane and this axial bond, this is basically 90 degree. So there is no problem. All the angles are 90 degree. See, one more interesting thing. Wherever all the angles are same, don't bother about to put lone pair or bond pair anywhere. And in that case, don't think about bend rule. Bend rule will be applicable when there will be two different types of bonds, two different types of groups. Okay? At that time you need to think about the positions of lone pair and the bond pair. Otherwise, no need to think about anything for this geometry. Well, sir, it means, see, if I put, is it okay? Of course okay. In that case, square plane base I will make like this. Okay. So it like same. If you put lone pair here, then how can I make the square plane base? Okay, I will make it like this way. 1, 2. Okay, this one and this one. No problem. So this is for this. This is the square plane base. This is the square plane, and this is the square plane. So no problem. Angles are same. Anywhere you can put. Question is sp3 for sp3d orbital. Now listen it very carefully. For sp3d orbital, what will happen? In the case of sp3d orbital, you cannot put lone pair and bond pair anywhere. What does it mean? It means that sp3d orbital is basically combinations of sp2 plus pd z square. This is pz and this is xy, px, py. This is the combinations. Now let me draw the geometry. Okay, no problem. So this is basically the sp3 hybridized orbital. Here two types of angles are there. You can see that this is 120 degree and this is 90 degree. Now here, if you calculate the percentage of S character here, okay, then what will be the percentage of S character in these equatorial positions? Okay, percentage of S character, I have just now written a formula. Cos theta is equal to S divided by S minus 1. So cos 120 degree equal to S by S minus 1 means minus half equal to S divided by S minus 1 means minus 2S minus okay, just a minute. Okay, minus half is equal to S divided by S minus 1. It means minus S plus 1 equal to 2S. It means 3S equal to 1. So S equal to 33.33%. Actually, this is the percentage of S character for sp2. Okay, no problem. From the formula we can calculate. Okay. Okay. So here percentage of S character is sp2. Percentage of S character is 33.3%. And here percentage of S character cos 90 0. So you can say the percentage of S character along the axial bond 0. Now you can say that this is the positions in sp3d geometry where lone pair will be happy because percentage of S character is more. Lone pair need more space. Lone pair is bulkier. Lone pair and double bond, group containing double bond, they need more space. So lone pair, bulkier, need more space, needs more space. So where you will put the lone pair? Okay, in sp3d geometry, I'll put lone pair in these equatorial positions and bond pair, more electronegative element in axial positions. Clear? This is the bend rule. Now after that I will discuss sp3d d3. Now let me finish this one. So in sp3d geometry, lone pair, equatorial positions and electronegative element, axial positions. Done. See, these equatorial positions and axial positions, it is for sp3d. Again I am telling that this is for sp3d. For sp3d it will be reverse. sp3d3 it will be reverse. So better to write that lone pair preferably occupy positions where percentage of S character is more and electronegative element where percentage of S character is less. Okay, this is now final. Done. So we have got these informations. Now go to the step. So how can we put SF4? How can we draw SF4? Okay, a straightforward I will draw. You just do by yourself hybridizations. I will do it quickly. SF4 beta how I will do? Okay, TPP. Here all are TPP geometry. So SF4, one lone pair. Okay, this is F, this is F. This is lone pair of electron. This is F. This is F. I told that lone pair will be in where? Equatorial positions. So done. Now, how about SF2CH3 whole 2? So now go to structure of SF2. SF2CH3 whole 2. Okay. First put S. One lone pair will be there. F most electronegative element, axial positions, lone pair here, ME, equatorial positions. Okay, done. See, there will be slight distortions in bond angle, like lone pair will become this one. It's a pi shape or K shape, right? Done. SR2 OR2. Okay, I put. Okay, this is S. Okay, R2 and OR2. OR will be here, more electronegative. OR, this is R, and this is the lone pair. Done. SR2 OR2. No problem. OR. SF2Cl2. Electronegativity of fluid is better than electronegativity of Cl. So based on these informations, what you will do? Let me show. Okay, S. Okay, if first you put electronegative element here, Cl here, and lone pair here. Done. Slide. Angle will be less than 90. This. Okay. Now SF3Cl. But SF3Cl S. Okay, put F here. Okay, one F here. SF3 lone pair equatorial, and this is SF3Cl. This is SF3Cl. Okay, clear? Okay. This color will use. Okay, done. Very. No problem. No problem. XCO2 F2. Okay. XC. What I told, that double bond also need more space. So F2 you put here. Double bonded O here. 1, 2, 3, 4, 5, 6. One lone pair. Put it here. Done. ClF3. Very simple. What you will do? ClF3. 1F, 2F, 3F, and 2 lone pair of electrons. 2 lone pair electrons, you put it here and you put it here. The angle will be less than 90 degree. It will be around 87 degree. 87.5. It will be around 87.5. Altogether it is 175. Okay, ClF3 done. XCOF2. Okay, XCOF2. Okay, let me take this one. XCOF2. So this is XCOF2. First put F here. Okay. O. This is double bonded O. So 1, 2, 3, 4. Lone pair 5, 6, 7, 8. Lone pair will be in equatorial positions and electronegative element in axial positions. And done. Okay. Now. Okay, XCF3. I'll draw. Okay, all the XE beta F. Okay, 1, 2, 3, 4, 5, 6, 7. So here one. Done. Okay, do you get my point? Okay, let me drink some water. Next what? XCF2. XCF2. This is Xc, more electronegative element here, here. Okay. Lone pair, 3 lone pair. You just calculate by yourself. Huh? From the total valence electron, after that divide by 8, you will be getting this information. Then I3 minus. Okay, I draw all structure shape for you. I3 minus sorry. Okay. I draw it here. This is central I. Okay, no problem. I3 minus lone pair, 1 lone pair, 2 lone pair, and 3 lone pair. This is minus. Okay, 2, 4, 6, 7, 8. No problem. ICN equal to minus. ICN equal to minus. Okay. I C triple bonded N, C triple bonded N minus 1 lone pair, 2 lone pair, 3 lone pair. 2, 4, 6, 7, 8. Done. Okay, IB at 2 minus also same. XCO3F2. Let me XCO3F2. See what I told, the lone pair, double bond need more space. So XCO3, double bonded O, double bonded O, double bonded O, more electronegative element F. Okay. sp3d 1 2 3 4 5 sp3d done. Okay. Now next more TBB geometry. Okay, PCl to F3, very interesting. PCl3F2. Okay, put F here, put Cl here, Cl here, F here. See, after you put the 2 F atom in the equatorial axial positions, then rest of the F you have to put in equatorial positions. Put F first 2 F in the axial positions, then rest of the F you just put in equatorial positions. Done. PCl3F2. Very simple. PCl3F2. This is P. This is a first put F. Okay, Cl. This is Cl. This is Cl. This is Cl. Done. Okay. Now what is this one? PCF3 roll to CH300. Okay. PCF3 roll to CH300. See beta, CF3. This is more electronegative. So PCF3, CF3. This is Me. This is Me, and 1 lone pair electron. Okay. 1, 2. PCF3 roll to CH3. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4. CF3. Okay. Do one thing. PCF3 whole to CH3 whole thrice. Do one thing. This one. So this is thrice. Otherwise you don't be. Okay. CH3 whole thrice. Do it like that. So what will happen? One more CH3 equation. Done. Okay. Now XeO2F4, XeOF4, ClF5, SF4, XeF4. It's a very simple. I will show you only one. XeF4. It's lone pair, you can put it in anywhere. XeF4. 1F, 2F, 3F, and 4F. And this is lone pair. This is lone pair. But lone pair you must put either at 120 degree at TBB, and in case of this octahedral geometry, you put it at 180 degree. 180 degree. Don't put lone pair here. It will be unstable. Don't put lone pair here and here. Okay, that won't be correct because lone pair repulsance is very significant and that make this molecule very unstable. So done. And last one, XZOF4. After that you just do it. XZOF4. XZOF4. Okay. XZ. Okay. Double bonded O F F F F and you just put lone pair here. See here all the 1, 2, 3, 4, 5, 6, 7, 8. Here all the angles are same. So you can put it as per your wish. It won't create any problem. Okay, double bond need more space. Okay, let me. Let's see. Long term, double bonded. If this is also okay, I think no problem. Okay, you can draw these points XCOF4. Okay, like that way you just draw the shape structure. Okay, 1, 2, 3, 4, 5, 6, 7, 8. No problem. Now move to another geometry. This one is like sp3d3. In sp3d3 all the angles are not same. See, sp3d3 all the angles are not same. I'll explain that one. See, in sp3d3 geometry, look at very carefully. In sp3d3 geometry, so this is central and okay. So this angle is 72, right? All the angles are 72 degree, and this angle is 90 degree. Okay. Now percentage of S character where it will be more. Percentage of S character will be more here because angle is more 90 degree. So more electronegative element in this case will occupy in axial positions. More electronegative element will be in equatorial positions in this case. So here I write here more electronegative element will be positioned where percentage of S character is less. Here percentage of S character is less. Okay. So here it will be in equatorial positions, and lone pair will be in axial positions because angle is more. Cos theta beta cos theta is equal to is divided by S minus 1. Theta increases, percentage of S character also increases. Your theta is 90 more than 9%. Okay. So here percentage of S character will be more and lone pair will be in axial positions and more electronegative will be in equatorial positions. Now go to the next slide. Sorry. Okay, previous. Okay. Now let me write you XCF5 minus 8 plus 5 into 7 plus 1, that will give you 44. So 8 5s are 40, 4 2 2s are 4, so 5 2s are 7 is an static number 7, and this geometry is sp3 d3. And where will be the lone pair? 2 lone pairs and 5 bond pairs. Lone pair will be in a position where S character is more. So lone pair will be in this case axial positions. So how I draw? Let me draw that one. Okay. Okay, theta. Okay, this is okay. This is exit. Okay, F5, 1F, 2, 3, 4, 5, and lone pair. Lone pair you just put it here, and the shape is, this shape is pentagonal, pentagonal. Okay, done. Let's see, F5 minus this is pentagonal. Okay, why is it? Do you get my point? You understand this? Okay. Now, I think structure related things I have mostly discussed. Thing is that there are two more things left. Two more things left. One is the comparison of angle. That will I will discuss later. That I will discuss later. I'll put it soon. A different angle in the same molecule means I am not going to discuss in detail now. Here, this angle and this angle will be different. This theta 1, say this is theta 2. Theta 1 won't be theta 2. Okay, this one I will discuss very soon. And one more thing, the bond angle bond length comparison. Let me take you or give you one example. In so this is H, this is H, and this is H, this is H, and in there are so many examples. There are so many examples. So if I need to compare the N and bond length, so this is x1, so this is x1 and this is x2. X1 not equal to x2. Okay, no problem. No problem. Okay. One more term I will tell, that is apicophilicity. That's it. But apicophilicity. Okay. What do you mean by apicophilicity? See, the phenomenon in which more electronegative elements in TBP geometry occupy in apical or axial positions, that is known as apicophilicity. The phenomena in which more electronegative element occupy in axial or apical positions is known as apicophilicity. Okay, apical positions is known as apicophilicity. Means is the apical positions. This is the apical positions. And here electronegative element will preferably occupy. This phenomena is known as apicophilicity. Okay. See, now if someone, I'll tell you only one thing, that if someone feels that instead of say CLF3, I'll take you the example CLF3, sometimes it will be confusing for you. From whisper, some of the students have interpreted CLF3 structure, I mean positions of lone pair and the bond pair a different way. Okay, that also I will explain in CLF3. But I told that 2 sigma, 3 sigma, 3 sigma pp plus 2 lone p. See, S bar and the bend rule here also give the same result. I mean positions. I will show you that. Let me put the lone pair and bond pair like CL. Okay, this is F, this is F, CL, F3. If someone try to put the lone pair here and here like pentagonal bipyramidal geometry, someone in square planar like 180. So someone may feel that, sir, here also it will be at 180 degrees, so it will be the stable. Why not stable? But bend rule says no. Lone pair must be in a positions or percentage of its character is more. So it contradicts. It won't be like that. You may feel that this won't be the correct one, but you may feel that at 180 that it will be the preferred structure. Lone pair repulsions will be minimum. But bend rule says that. Bend rule says no. Lone pair will be in the equatorial positions. Okay, one structure. One more structure, CL. Okay, someone may put it lone pair 1 here, one lone pair here. Okay, F here and F here. This is also one structure. And one more where I can draw. Okay, I'll draw it here. One more structure, I will draw it here. CL, lone pair, F, F, F. Okay, sir, this is the correct one you told. How we can say from the base part, like repulsions must be minimum. So here you just consider the 90-degree bond pair lone pair repulsions and lone pair repulsions, and you just count. Okay, let me show you that. See here how many lone pair, one pair 90-degree repulsions are there. Okay, I'll just show you. If you are not getting this one, I can show you. It's a very simple. Okay, see, if lone pair, I'll show you. Okay, you just look at here. I think you can. Okay, I think you can see it. Triangular plane, equilateral, and this is axial. Okay, how many 90-degree lone pair and bond pair? Sir, 1 90-degree, 2 93, and from bottom 1 2 3 6 90-degree lone pair, bond pair. 6 90-degree lone pair, bond pair repulsions. Sir, here how many 90-degree to each other? Okay, I'll put it here like that. Okay, you can see now it very clearly. So how many lone pair and bond pair? Check it. This is 90-degree. 1. This is 90-degree. 2. This is 90-degree. 3. Okay, and 190-degree, 90-degree. See, from here, from model you can see. See, this is 90-degree lone pair, 90-degree. So how many 90-degree lone pairs? This is the lone pair, one pair. 1 2 1 2, and here 3. So 3 lone pair, one pair, and 1 90-degree lone pair. Okay, 3 90-degree lone pair, bond pair, and 1 90-degree lone pair, bond pair. Now this one for this one. Okay, let me put it in equatorial positions. and let me count the 90-degree lone pair one pair, which is significant, and lone pair also. See here 120-degree repulsions, it's a very less insignificant compared to 90-degree. How many lone pair one pair repulsions you will get? Here 90-degree beta, you can see here 90-degree. Okay, no problem. Okay, check it here. See, one lone pair, one pair, one. Here 1, 2, and from bottom also say beta 3 and 4. So 490-degree lone pair, one pair. You got it? 1. Okay. And this one 2. Okay. This one 3. And one more. This one 4. Okay. So 490-degree lone pair, one pair repulsions. So which one will be the most stable? See, first of all, these won't be because here 690-degree lone pair one pair. It will be very unstable, compared to this one and this one. Here 4, total 4, and here also 4. So which one will be more stable? See, here 390-degree lone pair one pair, 190-degree lone pair one pair. Here 490-degree lone pair one pair, but 190-degree lone pair repulsions. This is very significant repulsions. This will make the molecule very unstable. So it won't be positioned here. So this will be the correct structure. So lone pair and one pair will be positioned in such a way or in such positions where the repulsions will be minimum. Okay. So this is the main rule about the writing the structure. I mean, get the definite shape of the molecule, and later I will discuss the angle and the bond length comparison. So thank you so much.